Hello, this is our FurnXpert Batch 2020. We have upgraded it quite a bit, and this is our latest FurnXpert Batch software. In our first FurnXpert Batch software, you can pretty much simulate or analyze any type of batch furnaces used in industrial application. These batch furnaces could be bogey hearth furnaces or any type of heat treating batch furnaces, whether it is a vacuum or atmosphere type of batch furnaces. In order to run this furnace application, you can enter the data directly on this form. So there are several tabs. There is this furnace data tab where you enter all your furnace data, furnace related data. And the way it is done, you can go for a rectangular batch furnace or you can go for a circular batch furnace. The circular could be both horizontal circular batch furnaces or a vertical batch furnace. So this is a horizontal one, this is a circular one. In addition to that, you have to enter all the data. For example, furnace dimensions, door information, slot, if there are slots inside the furnace, pier information. Piers are those support in which the products are resting. Then you have the refractory data. The refractory data comes with 4 tabs. There's a roof, the sides, ends, and the hearth. And if you notice, there is a list of refractory that is already entered in the database of this particular software. And you can either use them or you can enter your own data, refractory data, which I'm going to discuss a little bit later. Then you have got other inputs like other components. For example, if there are some other components that needs to be heated, if it is there, that's where you enter the data here. And then for atmosphere, this is where you enter the atmosphere data. And there is different types of atmospheric gases that you can select from. Then you have the option to run both either a combustion type of furnace or an electric type of furnace. So for combustion, you have got fuel type, burner type, fuel specification, for example, what type of fuel, air-fuel ratio, combustion air temperature, etc. Now, if you go to the electric type of a furnace, then you have got different types of element type you can select from. It will automatically fill in the resistivity, the length of the furnace. You have to, length of the elements you have to put in, the diameter you have to put in, and then you have to put in what type of electrical specification you have, whether it's a single phase or a 3-phase electric circuits with voltage and efficiency of the electrical system. So after that, you need to enter the part related data, which means what type of parts are being heated. So there are 2 options here. Either you can have bigger parts or you can select the smaller parts, which I'll show you when you click these other parts, you'll go to the smaller parts. For the larger parts, there are 6 options right here, or 7 options. And there are annular pipe, circular pipe, or circular cylinder, rectangular bars, then spheres, then annular pipe, which are pretty long. I'll discuss why we have got either long and short, and then cylindrical short for long parts or the rectangular long parts. The reason we have got the short and long is because, like, we do this heat transfer calculation, and in this heat transfer calculation, if it is a smaller if the length is relatively smaller compared to your width and height, you will find you need to use a different type of transient analysis. Then we go into either a 2D or a 3D analysis. For a longer part, you can either do a 1D analysis or a 2D analysis. So that's the reason why we have got this different type of an option that you can select different types of parts. Now, if the parts are really small, you don't have to go to this option at this time. Then you can go to this other part. And when you do the other part, you see there is another screen that pops up where you can select either rectangular bar, but these are relatively very small parts because we are doing a different type of transient analysis for this particular type of parts. And that's the primary reason we have separated them into different types of parts and things like that. So when you have say a batch furnace, which are primarily heat treating furnaces, smaller in shapes where you're heating small parts, then you can use this part selection option. And if you notice, there are also options whether you're putting the parts in a baskets or trays, or and the tray and basket information that you can put in. So after that, you have to go and put your boundary layer or boundary conditions. Boundary conditions are nothing but your furnace temperature, which is a time and temperature. So what happens in a furnace, you set up the time and you tell exactly what temperature is there at what period of time. So that's on that basis, the heat transfer program will be run. So right now I'll go and select a file. We can put all the data, but it will take a long time. So what I'm going to do, I'm going to select a file that where we have already entered all the data and saved them. So this is the one that we are going to open. And once we open that, you notice there are several types of inputs that already filled in. So this is furnace dimension of length 8 meters by 3 meters, 3.6 meters versus 1.9 meters. There are door areas here. And then we have got several refractory. Here we are selecting one refractory layer for all the sides. You can select either 1 or 4. Max you can do 4 or 2 or 3, whatever it is. We don't have too many data right here, not required, because it's a presentation or demonstration that we are giving about this particular software. But again, you can put them if you have to analyze those things. Here we are going with an electrical furnace just because that's what was done here. And if you notice, we have selected this element and then the resistivity, the length, which is a 1 meter length of furnace that's being selected, the diameter of 2 centimeters. Now, this is very important, number of elements. So if you see that, there is only one element right now, okay? So certainly in a furnace of this size, you cannot put one element. So there has to be several elements. So we'll go and say we'll put, say, something like 30 elements of each 1 meter long and 2 centimeters diameter. So we will go ahead and with a 3-phase delta, 400 volt is the voltage across, and then the efficiency is 80%. So we will go ahead and select this particular furnace. Now we have come to this particular screen or tab where you have where you see all the part related data are put in. Instead of using a rectangular short furnace or short part, we are going to use a cylindrical long part because this will run quicker. The other ones, it will take a longer time to run because the transient analysis takes longer time. So, okay, now here, if you see, like, there is the material tab or drop-down menu, and you can select several types of material: aluminum, brass, copper, tin, carbon steel, and whatnot. So we will go ahead and use a tin carbon steel, which is a very common product. If you notice, like, there is one, which is the boundary condition. The boundary condition is very important, primarily because that determines exactly how the heat is being soaked in, or how the heat goes inside your part. So either you have a view factor or you have the gas velocity. So if you have got a fan with a higher gas velocity, this number will be higher, where the view factors is primarily because of the radiation. Now, in our software, we use both the radiation and convection as boundary condition. Now, at a higher temperature, radiation predominates, whereas in a lower temperature furnace, the convection predominates. And this program knows about it and automatically does that calculation. So here we will go ahead and put a 10 centimeter diameter cylinder, and the length we will put 100. As you see, like, it's a long cylinder, and that's why let's make it pretty long. See, it's almost 1 meter long. You can even make it longer than that. So the initial temperature IT is 30. If you hover on this input, it will tell you exactly what it is. The number of cylinders that are being heated is 5. We'll make them 10 just to have more number of cylinder heated in the furnace, because it's a pretty long furnace, pretty big furnace. Only 5 is not a very optimum heating. So we'll put 10 right there. So the view factor is 1 and the gas velocity is 3. So we will go ahead and do a select. Then we come to this boundary condition. Now, either you can have a constant temperature, that means from start to end, it has the same temperature, or you can have a ramp like most of the batch furnaces. So let's go and heat this for 60 minutes, and it will ramp for 30 minutes, and then it will have a steady temperature from 30 to 60 minutes. So it will start from ambient 30 degrees C and go to 1000, and then hold to 1000 degree Celsius. That's all. Now with this, all you have to do, go and do a calculate. Once you do a calculate, you see this bar is going up, and you already have a nice graph where the red line is the temperature of the furnace. So it ramps up from 0 to 30 minutes and then holds constant from 30 to 60 minutes. And if you see, like, the part temperature slowly moves up. There are 3 lines right here. One is the center of the cylinder, one is surface of the cylinder, and the other one is midpoint between the center and the surface. So if you see, like, the surface will be heated first or more, and that's why it has got higher temperature. The center will be the lowest temperature, and the midpoint will be having a temperature in between the top and the center. So with that, the next thing that we need to run is the heat analysis, because right now what we have done, we have just run the thermal or transient analysis, how the parts are being heated. Now, with the parts being heated, we have to now run to find out exactly what are the heat requirements. So once we do the heat profile, so immediately it comes and it will give you the actual heat profile of the furnace. That means if you are heating the parts the way it is right here, the heat requirement will be like this. So if you notice, like in a Q total is the actual demand. And then because the furnace runs with a certain efficiency, the heat input will be much higher than the actual demand. So this is how the heat graph or heat plot is shown. It slowly goes up and then it comes to a point, which is exactly at the point 30 minutes. And then you really don't, like, the heat requirement goes down because it has already attained a certain temperature. The rate of temperature increase in the part has now decelerating. So this is the actual heat demand and the actual heat required. The next one is the heat to the part. This is exactly what is required if you, or the amount of heat that goes into heating up the parts. The next one is the actual heat that goes into heating up your refractories. Now, there are two components here. One is refractory store, the heat to the refractory stored. That means, like, how much of heat is going and getting stored in the refractory. The other one is the refractory heat loss. Now, if you notice, like, refractory heat loss steadily goes up and then becomes constant after some times. Now, after 60 minutes, it still will go up and things like that. So you still see a curve which is going up. On the other hand, your refractory store, a refractory heat store, it goes up to a point, just like heat to this parts or steel, and then it slowly comes down because now it's pretty much getting soaked and it doesn't need that much of heat to heat the refractories. The next is the skin temperature. That means the temperature of the refractory at the outside at the ambient. So it will exactly tell you how much, what temperature it has attained. Because if you need to have a certain temperature requirement, this will give you the exact temperature. Now, before I go any further, I will go and I will change the plot utility, because from here you can change the utility, like, the graph, like, how big, like, how much you want to see that, see the graph, like, if you want to change the scale of the graph and things like that, you can do it from here. So we will make it not an exponent. And then what we are going to do, say, for example, right here, the skin temperature, we'll make it 500 because it was not showing exactly how, because it was passing that temperature limit. So we'll go there, and if you notice that skin temperature, we are attaining somewhere around 400 on one surface, and the other surfaces are about 150. So these are all the heat bound. Then you go and see the amperage plot. Like, this shows exactly how much amperage is being drawn to heat this particular furnace at that temperature and at that profile. And then power density plot, then element temperature plot, which is again showing really high because it goes really high, much higher than your actual temperature. Let's see if I can change that uh, plot. That's the amp plot. Now we don't have it right now, so don't worry about it. So this amperage will also show a graph which is very similar to your heat plot. So this is the heating results. And then you go to the heat report. Here you see all the values. And then these are all the input data, the refractory data, part data. Right here is a heat audit, the amount of heat that goes into hitting the part, the average, maximum, and the total. And then you see wall loss, the wall storage, and then door loss. And then if you have got other losses, which is 0 here, it will be shown. And then it gives you the total heat demand and then the total heat input. And if you notice here, the electrical power is also shown here. The amperage, average amperage is 3,325, maximum is 6,663 amp. Element temperature max is 1946 degrees Celsius, and the element temperature is average is 1501. Now this will also vary if you vary your number of elements, then also the element length and element diameter. So this is all about heating. Now, if you want to go ahead and make it a combustion type of furnace, you can do that. All you have to do, say a conventional furnace, we will use natural gas as the fuel. The combustion excess air, we will do it 10%, and combustion air temperature to be something like 200 degrees, and fuel temperature of 30 degrees. If you notice, like, there is also a combustion air temperature as a function of furnace temperature. So if you have a combustion air temperature which varies with your furnace temperature, you can put that thing right here in this particular option. What happens is that comes out with a table, and you can put that values right here. The first column is furnace temperature. The second column is combustion air temperature. So we will not do that. We will go ahead and select a constant combustion air temperature of 200. And with that, we will go ahead and run the program again. So if you notice, like, it again shows you the part temperature. Now, if you go and do the field temperature, like, the heat profile temperature, here it will give you a certain Q gross temperature, which is much higher because combustion furnaces are much lower efficiency than an electrical furnace. So if you notice, like, here heat demand is much lower than your actual heat input. Similarly, you'll get the same plots right here. And then if you go to your heat report, now you see you have the combustion analysis, and this electrical power analysis was from your previous previous analysis, but this is what you really need, the combustion analysis that you ran for the second case. So that's all about your the heating cycle. Now you can go ahead and do a cooling cycle also in this furnace. In the cooling cycle, if you notice, like, what it does, it has, you have heated till 1000 degree Fahrenheit or Celsius. So now you are going to cool from 1000 degrees Celsius and say the total cooling time is 60 minutes. So we will go ahead and put the time temperature values, and then we will do a run. And if you notice, like, this is your furnace temperature. Again, it ramps down till 30 minutes and then holds steady for another 30 minutes. And this is a temperature of your part that is being heated. Here also, after you run the transient analysis, you can do a cool profile. And with cool profile, it will give you the amount of cooling that you need. So the red plot is the cooling that is required for your part, and the green is the cooling that you need for your refractory, and the blue line is the total heat that needs to be taken out, or the amount that needs to be cooled. So if you go to the cooling report, you see the same thing as the heating report. Here it gives you the cooling report, the wattage that is average, maximum wattage, and total watt hour. Similarly, for wall loss, you have the same thing, and there's a total cooling demand. So that's all about the analysis that you can do with this particular software. So to summarize, so what you have to do is that you enter your furnace dimensions and furnace data, you enter your part dimension and part data, you select your profile, and you run the analysis for heating. Similarly, for cooling, you have to you have to enter your cooling parameters. That means time temperature for cooling, and you run the analysis, and it will give you the temperature of the parts that when it is cool, along with the amount of cooling that is required. With that, the results are either in the form of report, as it shows here, or you can click to generate an Excel spreadsheet. So if you click here, an Excel spreadsheet is generated, and it shows right here. And if you notice, it has got all the furnace data, part data, and then time temperature profile, as well as all the heat that is required. You can even do a plot from here directly. Now I'm going to go into the other part of the software where you can put in data. There are refractory data that you can put in or edit or see. So there are several that has been entered already. But if you want to enter more data, you can just go ahead and put a new and then enter a data. Similarly, you can put in material data, and you can have a field data too. There is a steel property data, which is pretty much constant because we have got almost 26 steel grades, and that pretty much encompasses all the steel grades that you will need to run. So we haven't allowed entering of that data. So with that, like, you have got a help menu with each, you can see exactly how the software runs or how to run it and things like that. There are different tabs. And with that, you can pretty much know exactly how to run the software. That's pretty much it about the software. And if you need more information, please let us know. send us an email.